When we tally up every star, planet, and cloud of gas we can observe, we only account for about 5% of the universe. The rest is assigned to the dark sector, invisible substances that make up the vast bulk of reality, according to standard cosmology. We explain this immense unseen universe through isolated, separate mechanisms. Gravity emerges from the curving of spacetime. Dark matter is assumed to be an undetected, collisionless particle holding galaxies together. Dark energy is treated as a separate cosmological constant, continuously pushing empty space apart. We treat these dominant forces as entirely unrelated phenomena. We have an invisible particle pulling things inward and an invisible energy pushing things outward. They coexist in the same universe, yet share no underlying physical connection. The math works remarkably well to predict what we see through telescopes. Yet, to make those equations balance, we rely on patching the holes in our observations with completely distinct invisible entities, leaving us with a fractured picture of how reality actually operates. Dynamic vacuum field theory approaches the problem from a different angle. Instead of assuming the vacuum of space is an empty stage where physics happens, it treats the void itself as an active participant. To resolve the dark sector, we stop looking for undetected particles floating in the dark. We treat the vacuum as a dynamic physical medium, capable of bending, stretching, and fracturing. This vacuum field has two core properties. First is amplitude, which determines the stiffness of space and its resistance to movement, giving rise to what we experience as gravity and inertia. Second is phase, which controls how different regions of space synchronize and align. If the vacuum is a structured fabric, we drop the need for hidden particles to explain the forces we observe. We only need to look at what happens when that fabric warps and breaks under pressure, leaving physical strains and defects embedded directly into space itself. In the earliest moments of the universe, the vacuum existed in an unstable, highly symmetric state. It quickly underwent a violent transition, a tachyonic roll-down, shifting rapidly from that unstable state into a cooler, stable configuration. This drop in energy happened so incredibly fast that it outpaced the speed of light. Because causal information couldn't travel fast enough to tell one side of the universe what the other side was doing, the vacuum couldn't synchronize. Physicists call this a Kibble-Zurich phase-out event. Space shattered. The vacuum settled into localized pockets that were perfectly coherent inside their own borders, but violently mismatched wherever they bumped against a neighboring pocket with a different phase. The primordial universe was actively locking in permanent structural flaws. It wove frozen scars into the background of space that would dictate how all future matter would gather and evolve. Under this framework, we can abandon the idea of a dark matter particle entirely. The mass we attribute to dark matter actually comes from these frozen topological boundaries. Where the mismatched vacuum phases collide, they depress the field's amplitude, creating deep gravitational wells. These jagged boundaries act as massive sinkholes. Normal baryonic matter like hydrogen and helium fall in, pool at the bottom, and ignite into the spinning galaxies we observe today. But the vacuum never completely settled down. Even billions of years after the freeze-out, the fabric of space is still trying to iron out those mismatches and achieve global synchronization. The vacuum remains under continuous strain, pushing to align its broken phases. When we measure the accelerated expansion of the universe, we are measuring this exact residual synchronization pressure. Dark matter is the localized, frozen defect within the vacuum. Dark energy is the global drive trying to repair it. They are two symptoms of the exact same ongoing physical process. Dynamic vacuum field theory goes beyond mathematical abstraction. It makes specific, testable predictions about the structures we can capture through our telescopes. Because the vacuum is constantly working to relax its internal strain, those primordial defect wells should slowly stretch, widen, and smooth out over billions of years. If we look deep into the early universe, the vacuum hasn't had time to relax yet. Therefore, ancient galaxies forming inside those fresh, tight gravitational defects should look incredibly dense and physically small. This photograph from the James Webb Space Telescope captures precisely this era.
Looking at the magnified inset, we see deeply distant targets that are tightly bound and highly compact, perfectly matching the profile of unrelaxed vacuum defects. These deep space observations point to a universe that is slowly ironing out its primordial scars, rather than one defined by the static clumping of invisible particles. Gravity, inertia, dark matter, and cosmic acceleration all emerge from a shared origin. They are interconnected gears driving the ongoing relaxation of a single dynamic field. We no longer have to view our universe as an empty container filled with disconnected ghosts. Space itself has an active architecture. The cosmos is a continuous physical fabric. From the deepest galactic wells to the accelerating edges of expansion, it is simply trying to find its balance